Welcome to Lecture 15C, entitled Triple Integrals in Cylindrical Coordinates. And this is a set of examples, a second set of examples. And I just make a note here at the bottom before we go through it, that these examples have been covered in lectures before when we dealt with triple integrals in Cartesian coordinates. But you now have the tools to answer the integrals in a much simpler way using cylindrical coordinates. Also, this lecture contains worked out examples from the textbooks. You can skip this lecture if you were able to understand the homework examples. I probably just go in a little bit more detail here, so it's really up to you. Anyway, this material again comes from section 16.5 of the text and reading assignment 2 reference material section 3.2, which you're not responsible for. The objectives are to understand a select set of more difficult problems from the assigned problem set and previous quizzes and exams. The concepts and visualization skills here would be the integration bounds for radius r, angle theta, and z, how to determine them, visualization of bounding surface in cylindrical coordinates, and the differential volume in cylindrical coordinates. And as usual, the second slide is just a summary of the slides to follow, so we'll just move on. Okay, so now we're going to revisit a problem that we looked at when we dealt with triple integration using Cartesian coordinates. And I'm going to basically take the problem that we looked at before, but consider option 2 and see if we can formulate the problem in cylindrical coordinates rather than rectangular coordinates. So the objective is to compute the volume of the wedge of the cylinder x squared plus 4 squared equals 4 created by the planes y equals 3 minus x and y equals x minus 3. And so the option I've taken is to take the object and rotate it so that y is pointing upwards, but I make sure that z and x conform with the right-handed coordinate system. So everything basically is all right. Again, you can look at the URL if you want to play around with trying to visualize what the object actually looks like. All right, so the upper planar surface and lower planar surface are the bounds for y. Upper surface y equals 3 minus x, lower surface y equals x minus 3. Now notice here that I'm replacing z with y, where y is pointing upwards. So in fact, the polar coordinates now are with respect to the zx plane. So in defining basically a polar coordinate transformation here, we would say that r cos theta equals z, r sine theta would be equal to x, because y is now being chosen to be the z direction, but we call it y, of course. All right, so, just do not get hung up on symbols. The conventions need to be applied, and therefore there should be no issues. Okay, so as you'll notice here, we now have to figure out, all right, we're given the wedge of the cylinder x squared plus 4 squared equals 4z squared equals 4, and we're going to make a substitution of variables. And so what I'm going to do here is a little bit different. This is really sort of elliptical coordinates, not cylindrical coordinates, but it's cylindrical in the sense that it extends to infinity. So I'm going to make the substitution z is equal to r cos theta, and x is equal to 2r sine theta. Quite different. Now, if you substitute those expressions into the equation of the cylinder, you'll end up with r squared cos squared. You'll end up with 4r squared sine squared plus 4r squared cos squared. So the cos squared and sine squared basically just become 1. And so you end up with 4r squared equals 4 or r squared equals 1. And r can then range from 0 to 1, and theta can range from 0 to 2 pi. So effectively, using that transformation, we're able to sweep out every single point defined by that ellipse, x squared, elliptical cylinder, x squared plus 4 squared equals 4. All right, so that was a suitable choice based on the fact that I was dealing with something that was elliptical. Now, if the z equals r cos theta, x equals r sine theta, then it would have been circular. So there is a bit of a twist here. And this is, by the way, not done in the book. This problem was not solved in cylindrical coordinates, but I am, just to basically put a little extra twist on it. All right, we've also basically obeyed the conditions of a right-handed coordinate system, so there are basically no issues here whatsoever. So now that we've done that, we can basically compute a Jacobian and compute what the differential volume would be. All right, so if you do that Jacobian calculation, you'll end up with a value of 2r now. And so in this case, the integration order would be dy, and then dr and d theta. So that's the transformation that we see going from Cartesian volume element to this sort of cylindrical / elliptical coordinate. It looks like this. So the only thing we have to do now is to transform the bounds on y into cylindrical or quasi-elliptical. And so what we've done is basically taken the x minus 3, x is now 2r sine theta, and this was 3 minus x, so this is 3 minus 2r sine theta. So now this basically is in a form which is suitable for cylindrical coordinates, cylindrical / elliptical. This was a range for r, we've already decided, this range for 2 pi. So these three together define basically the domain enclosed within that cylindrical wedge. But again, we've done this by changing coordinate systems. Notice here the 2r, I relate that to the determinant of the Jacobian matrix. All right, so we put in the limits for y, which were upper bound and lower bound, that comes directly from here. The limits on r were from 0 to 1, and the limits on theta for 0 to 2 pi. And then the Jacobian was just this term that you see here. If you do this integration, which is a relatively simple integration compared to what we had to do when we dealt with a Cartesian coordinate system, the answer becomes 12 pi. If you want to visually see what we're doing in terms of trying to bound the domain using surfaces, then if you look at this picture, and you can look at it at this link here, this slider T that you'll find in this thing basically allows you to rotate this blue rectangle or half plane around in a full circle. The top and bottom surfaces are in red, and the front and back surface, like the yellow that you see here basically, would be representing the middle integral. So that would be the surface involving r, where r basically is fixed. Theta can take on any value, z can be any value. So this would be the ellipse that you see, elliptical cylinder. This is the top, this is the bottom, and this is the one that traces out the value of theta, and so you're sweeping out the domain contained within that wedge. All right, so here's another example, again from the book. Find the equation for the bounding surface, set up a volume integral, and evaluate the integral to obtain a volume formula. So it's a spherical cap with a radius r and a height h. The equation of the sphere, we can basically write that out immediately, is x squared plus y squared plus z squared equals r squared. And we're going to solve the problem in cylindrical coordinates. So in this case, again, x becomes r cos theta, y becomes r sine theta. So the upper bound on z is obtained by substituting the expressions for x and y, that's these expressions, into the equation of the upper surface and solving for z. So that means I just put it into this equation, solve for z, and I end up with this expression here, r squared capital minus little r squared. The lower bound on z is obtained from the picture. So this height here will be this radius r minus this height h. So that's the lower bound on z. So we got upper bound and lower bound on z. All right, what about r? Okay, what is going to be the upper bound on r? It's determined by equating the expression for the upper and lower surface, that's this one and this one, and solving for r. So if I equate these two, which is what I've done here, you'll find that the result is r equals the square root of this expression. The lower bound for r is going to be 0. So effectively, the r you're looking at is this region that you see here, projected on the xy plane. That's the intersection line there. And the radius of that would be this value that you see here. The range on theta will be a full circle, which is from theta from 0 to 2 pi. All right, so now I can put everything down. This, of course, is our differential volume. This r is the determinant of the Jacobian matrix. Lower and upper bound on z, lower and upper bound on r, and the bound on theta. And so now we can set up the integral. All right, so continuing from the previous slide, we had set up the integral so that we have the bounds for the inner integral, the middle integral, and the outer integral. And so now it's just a matter of doing the calculations. Again, let's look at an interpretation as to what these bounds represent. So if we look over here, this is basically between two surfaces, defined as z is defined as square root r squared minus r squared, and r minus h, upper bound and lower bound. And again, this is basically a triple integral, and in terms of cylindrical coordinates. The middle integral is between bounds of r equals 0 and r square root of 2rh minus h squared. And the outermost integral bounds are between 0 and 2 pi. So again, in this case, this is for r, which means z and theta basically take on any value within the domain. And this is from 0 to 2 pi, which means r and z take on any values within their own domain. And these are basically two functions, which are z. Again, theta in this case takes on any value within its domain, which is from 0 to 2 pi. So let's look at this diagram down below to show basically what these surfaces look like. So this would be z equals square root of r squared minus r squared. So that defines this upper pink dome that you see here. And r minus h defines this pink flat plane that you see, which sits a certain distance above the z equals 0 plane. The middle one is between r equals 0 and r equals 2r h minus h squared, which is basically this yellow cylinder that you see here. So that's essentially from 0, which would be like a line, a filament, all the way out to here. So those are basically the two surfaces associated with the middle integral. And the last one is between theta 0 and 2 pi, where in this case r and z can take on any value, where r, of course, must be greater than or equal to 0. And so that defines a plane. And all we're doing is sweeping this plane once around to make a full circle. So essentially these surfaces that we're dealing with here, 0 would be this, and 2 pi would come full circle once around and basically line up with this one. So a combination of those three define basically the region or the domain over which the integration takes place. Anyways, this you can look at in more detail as this particular link that you see here. All right, so let's basically look at another example. So this is to calculate the volume between the sphere, which is this part, x squared plus y squared plus z squared equals 19, and the hyperboloid, which at least one section of the hyperboloid, which is z squared minus y squared minus x squared equals 1, z is greater than 0. So obviously we're only talking about the top portion here. There's another flip side on the bottom side. All right, domain in cylindrical coordinates, that means we'll use the transformations x equals r cos theta, y equals r sine theta. The upper bound on z is obtained by substituting the expressions for x and y into the equation of the upper surface, which is basically this one here, and solving for z. And you end up with this answer. The lower bound on z is obtained by substituting the expressions for x and y, again these, into the equation of the lower surface, which is this one, and solving for z, in which case you end up with this answer. The upper bound on r, on the other hand, is determined by equating the two expressions, the upper and lower, which essentially gives us this boundary line that you see here, right, and solving for r. So if we do that, it means we're equating 19 minus r squared with 1 plus r squared, and the result is going to be r equals 3. The lower bound for r is 0, and so now we have bounds for r, we have bounds for z. Lastly, theta is going to be full circle, so that's from 0, theta from 0 to 2 pi. Putting it all together, we have to compute the Jacobian, determinant of the Jacobian matrix, which again will be r. This is classically the same value for cylindrical coordinates. Here are the bounds on z, bounds on r, bounds on theta. We can now set up the integral. Okay, so here are the bounds. We're basically integrating with respect to z, top and bottom surface, with respect to r, which is the region, and from 0 to 2 pi. And if you do this, you calculate this result. If you go back and when we looked at rectangular coordinates or Cartesian coordinates, it was a more complicated problem to solve. Here, this turns out to be a relatively simple integral. Again, if we want to look at the bounding surfaces, then I've shown them here. It's a perfect cylinder. That means that for a particular value of r, which is the point of intersection here, the full value of theta and all possible values of z. This is the upper surface, this is the lower surface, and then when we sweep out theta, what we're doing is we're basically holding theta fixed. R can be anything greater than 0, and z can be any value to plus or minus infinity, so we're dealing with a half plane. So if you basically click on the slider T in the interactive simulation, this blue rectangle just sweeps around and forms a full circle. What are we doing? We're going to basically be sweeping out the volume enclosed between that surface and this outer perimeter surface. All right, so the last problem we're going to look at is this one. Again, this is from the textbook. We have one sphere centered at the origin, which has a radius of capital R, and another sphere centered at 0, 0, small r, and has a radius of r where r is greater than capital R over 2. What is the volume of the region common to the two spheres? All right, so I basically, because this is a symmetrical problem, we can basically draw traces. So that means we just cut basically through the whole object. And what we would see, independent of how we slice it, where the plane is always going through the origin, and this would be a perfect example of what we would see. So this is basically the circle which is off-centered. So it basically has a radius of r, and this distance is r, which means it just touches the xy plane. And then we have the circle which is centered on the origin with radius capital R, which is what you see here. Because it's cylindrical coordinates, we can pick off points on the contours. This will be the radial direction, this will be the vertical direction, so that allows us to pick off points on that circle. The red basically would be radial, vertical, that picks off points on this outer circle. And the region of interest is between this black line and this red line. So it's this region right in here that we're interested in computing. All right, so this is basically a trace, and it's a cross-sectional view of the intersecting sphere. This URL will give you basically you can rotate the image. Sometimes it's difficult with these things that you see here. So this will be with respect to an upper surface when you look at the 3D perspective diagram, and this would be the lower surface if you were to look at this as a 3D perspective diagram. So the upper surface basically, which is going to be this one, is just part of the sphere centered on the origin, radius capital R. So you can express that in terms of r squared minus x squared minus y squared. The lower surface, which is basically going to be this one here, this one basically we have already gone through the derivation of it. So if you want to refer to it, it's in lecture 11b. That lower surface had an equation r minus square root of r squared minus x squared minus y squared. And so we have z here in terms of x, y's. And so now the question is, we'd like to solve this problem in cylindrical coordinates. So the next step basically is to actually do the calculation in cylindrical coordinates. We have basically used the symbols capital R and small r, so we cannot use them again. And so in this case, the coordinate transformations are going to be in terms of rho instead. So you'll quite often see that we run out of symbols and we just have to use something else. So in this case, x equals rho cos theta, y equals rho sine theta. The upper bound on z is obtained by substituting the expressions for x and y we basically had previous slide into the equation of the upper surface and solving for z. If we do that, we end up with the expression that you see here. For the lower bound on z, you get that by substituting the expressions for x and y into the equation of the lower surface and solving for z, and you end up with this expression. The upper bound on rho is determined by equating the expressions for the upper and lower surface, that's these two, and solving for rho. So solving these, we end up basically with rho having this form. The lower bound for rho will be 0. And then for theta, basically, since we're performing a full circle, theta will be between 0 and 2 pi. So now we can put all the pieces together. And here we have, of course, the differential volume in cylindrical coordinates, now in terms of rho rather than r. Here are the lower and upper bound on z, the lower and upper bound on rho, and the lower and upper bound on theta. And so now we basically can set up the integral, right? And make the substitutions. This the limits on z, limits on r, limits on theta, and we end up with this result, which is the same as the result we obtained working in Cartesian coordinates. So in this case, basically, we would end up with surfaces that look like this, which for the theta, basically would have this rectangular plate, which basically would complete a full circle, and you can use slider T to do that for you. You have the upper surface here. The lower surface is not quite visible, but it's underneath. Again, if you click on this link here, you'll be able to get a better view of it. And then, of course, the middle integral, which would be this outer cylindrical surface. All right, so there is one more here, which is the last one, which is to compute the volume from the wedge cut from the cardioid cylinder, where r is 1 plus cos theta. And we're talking about the plane z equals 2 minus x and the plane z equals x minus 2. Now, I've drawn the picture below. In fact, you can access it to the link, but probably for your own benefit, since you have to sketch it, you should draw a number of traces. So for example, z equals 2x and z equals x minus 2 intersect on the cardioid boundary. So, that will be useful to show to yourself. Also, r equals 1 plus cos theta has a non-negative r. So you're not going to have any issues in terms of problems with this function. So you constantly have to worry to make sure r doesn't go negative, because of course that's not possible, because r is defined only to be greater than or equal to 0. All right, so the solution to this problem, again in cylindrical coordinates, is just a substitution: x equals r cos theta, y equals r sine theta. And so in this case, bounds are given. So we have the bounds here, z equals 2 minus x. And the only thing we have to do is to replace x by r cos theta, and also the x with r cos theta here. So that gives you the upper bound and the lower bound. R is already given, so that's the upper bound. 0 would be the lower bound. And theta is full circle. So again, from theta of 0 to 2 pi. We need the Jacobian determinant of the Jacobian matrix, which again for cylindrical coordinates is r. And so we have all the values we need, so we can basically plug them into the bounds for the integral. So these are the bounds for z, this is the bounds for r, and the bounds for theta. If you do this calculation, you get 7 pi over 2. And again, in this case, if you want to basically look at the bounding surfaces, you have the red and the bottom, which are actually planes, and that would be two bounding surfaces. That would be for the inner integral. And then you have this yellow one, which would be an actual cylinder that goes to infinity, right? And that basically would be the surface representing the middle integral. And finally, the blue plate that you see here, which is a half plane, this will rotate, it's determined by the slider t, full 360 degrees. That sweeps out the angle theta. And again, in this case, since theta is fixed, r can be any number, though it goes out to infinity, and z can go to positive or negative infinity. All right, so that concludes Lecture 15C. Thank you for watching.